One of our viewers dropped a comment that reads like a fever dream of nested questions. Can planets be binary? Can a binary planet share a moon? Can moons themselves be binary? And the final boss, could a binary planet system share a binary moon, all of it orbiting a binary star? The answer is genuinely surprising because it takes us right to the heart of how gravity actually works at cosmic scales. And it shows us that the universe is far less tidy and far more weird than any textbook gives it credit for. Let's take it one step at a time. Before we can talk about shared moons, we need to nail down what we mean by binary planet. You won't find an official definition in any astronomical dictionary. The International Astronomical Union hasn't adopted one yet. But scientists generally agree on a useful criterion, and it comes down to one key word: barycenter. The barycenter is the center of mass of a system. When Earth and the Moon pulls on each other, it's not like the Moon just circles a perfectly still Earth. Both bodies actually orbit their shared center of mass. The catch is that Earth outweighs the Moon by about 81-1, which pushes that center of mass deep inside Earth itself, about 2,900 miles from Earth's center. The Moon is technically orbiting a point buried in Earth's mantle, invisible and underground. That asymmetry, most astronomers say, means Earth and the Moon don't qualify as a binary planet. There's a clear hierarchy. Earth is the planet, the Moon is the satellite. But what if the barycenter sat outside both bodies, floating in the empty space between them? Then you'd have a genuinely symmetric, genuinely double system. And that's exactly what happens with Pluto and Charon. Charon is Pluto's largest moon, and it's about 12% of Pluto's mass, proportionally far beefier than our moon is compared to Earth. The result? The Pluto-Charon barycenter sits about 600 miles above Pluto's surface, out in empty space between the two bodies. Pluto and Charon both orbit that empty point, like two ice skaters holding hands and spinning together. Is that a binary planet? By the barycenter outside criterion, yes, except that when the IAU demoted Pluto to dwarf planet in 2006, it also declined to classify Charon as a co-dwarf planet or satellite, leaving the whole thing in a definitional limbo that planetary scientists still find annoying. Among the full-fledged planets of our solar system, none of them cross this threshold. Earth-Moon comes closest, but no cigar. Out in the wider universe of exoplanets, though, the possibilities are wide open. Theoretical models and computer simulations show that two similarly massed planets can co-form in a protoplanetary disk and end up orbiting each other. We haven't confirmed one definitively yet. The transit method we rely on makes it hard to tell a binary planet from a planet with a big moon, but there's nothing in the physics that says it can't happen. So, binary planets can exist. Good. Now the real question, can two planets share the same moon? Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. To answer this, we need to introduce one of the most useful concepts in orbital mechanics, the Hill sphere. Every planet has a gravitational reach, a zone where its pull dominates, but that zone isn't infinite. The further you get from the planet, the more the star's enormous gravity starts to disrupt things. Beyond a certain distance, any satellite's orbit becomes unstable. The star's perturbations build up over time until the object drifts away. The roughly spherical region within which a planet can stably hold onto its satellites is called its Hill sphere, named after the American mathematician George William Hill, who worked it out in the 19th century. Earth's Hill sphere has a radius of about 930,000 miles. The Moon orbits at just 230,000 miles, comfortably inside. In practice, stable satellite orbits extend to maybe a third of the Hill sphere radius before long-term perturbations become a problem, so roughly 300,000 miles for Earth. Now, in a binary planet system, the Hill sphere doesn't belong to one planet or the other. It belongs to the whole system. From a distance, the binary pair looks like a single combined mass orbiting the star. So the system as a whole has a Hill sphere, set by the total mass and the distance from the star. Inside that overall hill sphere, each individual planet also has its own smaller hill sphere. That means a moon in the vicinity has three possible situations. Scenario A, bound to one planet. The moon orbits snugly around one of the two planets, well inside that planet's individual hill sphere. It doesn't really belong to the binary system as a whole. It belongs to one of its members. The other planet is basically a bystander, though it does produce perturbations that can slowly destabilize the orbit over geological timescales, but that's a story for another day. Scenario B, a circumbinary moon. The moon orbits both planets together on a wide orbit that wraps around their common center of mass. This is the true shared moon. This is where things get really interesting. Numerical simulations show that circumbinary orbits that encircle a binary system, can absolutely be stable, but only if they're far enough out. The rule of thumb, backed by decades of orbital stability research, is that a circumbinary orbit needs a radius at least 2 to 3 times the separation between the two planets. So if our binary planets are orbiting each other at, say, 60,000 miles apart, a shared moon would need to sit at least 120 to 180,000 miles from their barycenter, and it would still need to stay inside the system's hill sphere relative to the star. If both conditions are met at once, the shared moon is stable. And here's the thing. This isn't just theoretical. The Pluto-Charon system has, in addition to Charon, 4 smaller moons: Styx, Nix, Kerberos, and Hydra. All 4 orbit at distances far beyond Charon, encircling the Pluto-Charon system as a whole. They are, in every meaningful sense, circumbinary moons of a binary planet. They exist right now in our own solar system, and the New Horizons spacecraft photographed them up close in 2015. So, yes, a binary planet can share a moon. We have real examples. The 4 small moons of Pluto are exactly that. Here's the question that went viral in astronomy circles back in 2018. Can moons have moons? Researchers Juna Kohlmeier and Sean Raymond published a paper with a delightfully playful title, systematically working out the conditions under which a moon could have its own stable satellite. They called it a submoon, but the internet immediately latched onto moon, and the technical term never really had a chance. The logic mirrors the hill sphere argument. A moon, like any other body, has its own gravitational reach. If that reach is large enough and shielded enough from outside disturbances, mainly the host planet's gravity and indirectly the stars, it can hold a stable satellite of its own. Kohlmeier and Raymond found that the key ingredients are simple. The moon has to be big, and it has to orbit far from its planet. Bigger moon equals larger hill sphere. More distant orbit equals less disruption from the planet's own tidal forces. When they ran the numbers for our solar system, the results were striking. Earth's moon, given its mass and orbital distance, could theoretically host a stable submoon out to about 185 miles. Tiny, but non-zero. Saturn's Titan could host a submoon out to roughly 25,000 miles. Even Callisto, the outermost of Jupiter's 4 Galilean moons, could host a stable satellite. None of them actually do, probably because the chaotic early history of the solar system swept those orbits clean long ago, but the physics allow it. A binary moon is a slightly different beast. It's not a moon with a submoon, but 2 moons of similar mass orbiting each other, with their shared barycenter then orbiting the planet. The stability requirements are even stricter, because the planet's tidal forces work hard to pry the pair apart. But again, the physics doesn't forbid it. It just demands that the 2 moons be massive enough, close enough to each other, and far enough from the planet. We haven't found one yet, but detecting moons of exoplanets is already incredibly hard. Right now, we have exactly 1 exomoon candidate ever, Kepler 1625b I, and even that one is still contested. A binary exomoon would be essentially invisible with current technology. Now we put it all together and arrive at the most vertiginous question of the lot. Could a binary planet system share a binary moon? Let's build this thing mentally. We have 2 planets, call them P1 and P2, similar in mass, orbiting each other with their barycenter out in the space between them. That's our binary planet. The whole system orbits a star. Now we take 2 bodies, also similar in mass, orbiting each other. That's our binary moon. Their barycenter then orbits around the center of gravity of the double planet on a circumbinary orbit. Let's try to picture it. Two similarly sized planets orbiting each other, their barycenter hanging in the empty space between them, as we've seen, and circling around them, two moons also paired up, locked in orbit around each other while together they loop around the two planets. It's a house of cards, and for it to hold, everything has to work at the same time across different scales. Two moons need to be close enough to each other to stay bound by their mutual gravity, but far enough from the two planets not to be torn apart by their gravitational tides. The moon's orbit around the planets need to be wide enough, at least 2 to 3 times the distance between the planets themselves, but not so wide that it crosses out of their Hill sphere, that invisible boundary beyond which the star starts calling the shots. And then there's time. Billions of years of tiny perturbations, of orbital resonances slowly building up, that can turn a perfectly stable system into an excruciatingly slow motion train wreck. Every level has to fit inside the one above it, like Russian nesting dolls, but if one is just a little too big, nothing closes. That's a delicate balance across 4 nested levels: star, binary planet system, circumbinary orbit of the binary moon, mutual orbit of the two moons. Each level has to be stable relative to the one above it. Numerical simulations of hierarchical multi-body systems, an active field in computational celestial mechanics, suggest that configurations like this can exist within specific windows of parameters, but they're vulnerable to orbital resonances. A resonance is when orbital periods fall into simple integer ratios, 1 to 2, 2 to 3, and so on, causing gravitational nudges to add up rather than average out over time. A system this intricate has many more ways to stumble into a destabilizing resonance than a simpler one. That said, delicate and rare is not the same as impossible. In a universe with hundreds of billions of galaxies, each containing hundreds of billions of stars, the sheer statistics suggest that even highly unlikely configurations that don't violate any physics probably exist somewhere. Our viewer adds one final layer, and it might be the most beautiful one. What if this entire system orbited a binary star? Binary stars are remarkably common. Roughly half of all stars in the Milky Way are members of multiple star systems. Our Sun, orbiting alone, is actually the odd one out. Stable planetary orbits around binary stars come in 2 flavors. P-type orbits, circumbinary, the planet orbits both stars together, with the stars sitting well inside its orbit. The planet wraps around the whole pair, exactly like Tatooine in Star Wars. This is real. The Kepler Space Telescope confirmed a dozen circumbinary planets, including Kepler 16b, Kepler 34b, and Kepler 35b. These planets orbit stably as long as they stay at least 2 to 3 times farther from the stellar pair than the stars are from each other. S-type orbits, around one star only. The planet orbits just one of the 2 stars, while the other is far enough away to only weakly perturb things. These exist too. Alpha Centauri, our nearest stellar neighbor, just 4.37 light-years away, is a binary system, and models suggest it could host planets in S-type orbits around each of its components. Now picture taking the entire Rube Goldberg machine we built, binary planets hosting a circumbinary binary moon, and dropping it into a P-type orbit around a binary star. The hierarchy looks like this. Level 1, 2 stars orbiting each other. Level 2, the binary planet system in a wide circumbinary orbit around the stellar pair. Level 3, the binary moon system in a circumbinary orbit around a binary planet. Level 4, the binary moon orbiting each other. 4 nested levels of orbital hierarchy. A clock inside a clock inside a clock inside a clock. Researchers like Georgia Karakos and Filat Lohinger have studied the stability of planets in binary star systems and of moons in binary planet systems in some depth. The general finding is that stability is achievable but requires the scales to be well separated. The stars close together relative to the planetary orbit, the planets close together relative to the moon's orbit, the moons close together relative to their own size. Think of Russian nesting dolls. Each layer has to fit neatly inside the previous one with enough breathing room that the edges don't touch. A system of this kind, binary planets with a binary moon around a binary star, is physically permitted by the equations of celestial mechanics. It's not forbidden, it's just rare, fragile, and probably vanishingly uncommon in the real universe. But in a cosmos of 400 billion galaxies, vanishingly uncommon can still mean millions of examples. The obvious follow-up question: if these systems can exist, why haven't we spotted one? The blunt answer: our instruments aren't sensitive enough, not even close. Finding an exoplanet is already hard. The two main techniques are the transit method, the tiny dip in starlight when a planet crosses in front of its star, and radial velocity, which picks up the slight wobble a planet induces in its star. Both require years of precise measurements to detect an Earth-sized planet. Finding an exomoon means hunting for a signal buried inside a signal that's already barely detectable. The one exomoon candidate we have, Kepler 1625bi, flagged in 2018 by Tichy and Kipping, is Neptune-sized, which is enormous for a moon, and it's still not confirmed. A moon the size of our own moon, orbiting an Earth-sized exoplanet, is completely out of reach with current technology. A binary moon, or a full nested hierarchy like the one we've been describing, is so far beyond current detection capability that we can't even make a meaningful estimate of how common it might be. The absence of detections tells us nothing about existence. Upcoming missions may start to change this. ESA's Plato telescope, set for launch in 2026, is designed to find Earth-like planets around Sun-like stars with significantly better precision than Kepler. A future mission specifically targeting exomoons could push further still, but we're in the early innings here. Let's circle back to the original question and stack up the answers. Binary planets exist. We can see them in Pluto and Charon right now. Shared moons exist. Pluto's 4 small moons are genuine circumbinary moons of a binary planet. Binary moons are physically allowed by the laws of orbital mechanics, even if we haven't found one yet. A binary planet sharing a binary moon is physically possible. Delicate, demanding, probably rare, but not prohibited. And all of it can orbit a binary star. Circumbinary planets are already confirmed, and their satellite systems obey the same physics as everything else. The universe, it turns out, has no particular preference for simplicity. Give gravity enough mass, enough space, and enough time, and it builds nested structures that look like they came out of a mathematician's dream. Somewhere out there in a galaxy we'll probably never visit, 2 moons may be orbiting each other while together circling a pair of planets that are themselves dancing around 2 suns. Nobody's seen them yet, but the physics says they're allowed to exist. Okay guys, so what do you think? Did watching this video raise any doubts or questions? Let us know in the comments. And if you want to learn more about this topic, don't miss on the end screens, can moons have moons?